Shear and moment equations. In the previous lectures, we talked about shear and bending moment in beams and how to calculate them at specific points. For example, given this beam, we can determine shear and moment at C by first determining the support reactions and then by cutting the beam at C and writing and solving the equilibrium equations for segment AC. Since shear and bending moment may not be constant along the length of the beam, we need to be able to either express them mathematically or graphically so that their maximum and minimum values can be readily determined. In this lecture, we focus on the mathematical representation of shear and moment in beams. Once we have the necessary equations, we can then graph them in order to visualize how shear and moment change along the length of the beam, and more importantly, to locate the points at which these internal forces attain their maximum and minimum values. Consider this steel and glass building, designed and constructed to serve as an art center. Let's highlight 3 specific beams in the skeleton of the structure, each subjected to a different loading case. We are going to show how to write the shear and moment equations for each beam. We use the beam on the second floor to formulate the shear and moment equations due to concentrated loads only. For the short beam on the first floor, we end up writing the shear and moment equations due to a uniformly distributed load. And the beam on the side of the building covers the case of a partially distributed load combined with a concentrated load. In this presentation, we are going to assume that all 3 beams are simply supported. Let's start with the long beam on the second floor. Suppose the concrete roof panel, shown in green, is supported by 2 transversal beams only. This means that the weight of the panel is going to be distributed to the 2 beams. Assuming that the specific weight of concrete is 24 kilonewtons per cubic meter, the roof thickness is 229 millimeters, the length of the red beam is 10 meters, and each of the 2 transversal beams has a length of 3.5 meters, then the uniformly distributed load on each beam is going to have a magnitude of 27.48 kilonewtons per meter. The distributed load magnitude is the product of the specific weight of concrete, the thickness of the roof panel, and half the length of the long beam. If we multiply the magnitude of each distributed load by the length of the transversal beam, we get the total load per beam. If we divide the total load by 2, we get the magnitude of the concentrated load that is being exerted on the red beam, which is equal to 48 kilonewtons. Assuming that the beam is simply supported, we are now ready to analyze it and write its shear and moment equations. First, we need to calculate the support reactions. The free body diagram for the beam embodies 3 unknown reaction forces. Using the static equilibrium equations, we can determine the unknown forces. They are AX equals 0 and AY equals BY equals 48 kilonewtons. Note that the 2 applied loads divide the beam into 3 segments. This means that we need to write 3 shear equations and 3 bending moment equations, a pair of equations for each segment. Imagine that the x-axis runs along the length of the member with the origin of the coordinate system being located at the left end of the beam. So our equations are going to be written in terms of x. For each segment, we are going to cut the beam at some distance x from the origin, draw the relevant free body diagram, and then write the equilibrium equations so that we can express shear and moment in terms of x. For the left segment, we cut the beam at an arbitrary point between 0 and 2.5 meters. We label the distance from the left end of the segment, the origin, to the cut point as x, where x is defined between 0 and 2.5 only. At the cut point, we draw a shear force and a bending moment. These are drawn in the positive sense, meaning shear is acting downward and bending moment is acting in the counterclockwise direction. This notation is consistent with our sign convention, according to which a positive shear tends to rotate the beam segment in the clockwise direction and a positive moment causes a concave up deformation. Now we write the two equilibrium equations. The algebraic sum of the forces in the y direction must be 0, and the sum of the bending moments about point A must be 0. Solving these equations for V and M, we get. Note that in this case, shear is constant throughout the entire segment. Shear is not a function of x. Bending moment, on the other hand, does vary with x. Now that we have the shear and moment equations for the left segment of the beam, we are ready to write a similar set of equations for the beam's middle segment. Cut the beam at some arbitrary distance from the origin and label the length of the segment x. Here, too, we are going to show shear and moment at the cut point as V and M. We can get the shear and moment equations for the segment by writing the equilibrium equations and solving them for V and M like this. This pair of equations tells us that throughout the middle segment of the beam, shear is 0, while bending moment remains constant. Finally, to write the shear and moment equations for the right segment of the beam, we cut the beam at some distance x from the origin, where x is between 7.5 and 10. Then, we write the equilibrium equations and solve them for V and M. Here are the shear and moment equations for the right segment of the beam. In summary, given that the concentrated loads divide the beam into 3 segments, we must express shear and bending moment in a piecewise manner using 3 equations. Note that for each bending moment equation, the interval within which x is defined contains its boundary values. For example, the first bending moment equation is valid for any x value between 0 and 2.5, including at 0 and 2.5. However, the first shear equation is valid only for x values greater than 0 and less than 2.5. Why? Because shear cannot be defined at the point of application of a concentrated load. So for the left segment of the beam, shear does not exist at x equals 0 and x equals 2.5, where concentrated loads are present. The same principle applies to the other beam segments. For the middle segment, shear does not exist at x equals 2.5 and x equals 7.5, and shear is non-existent at x equals 7.5 and x equals 10 in the right segment of the beam. Now, let's examine the short beam in the front of the building. A 350 millimeter thick concrete slab rests partially on the beam, which is 6 meters in length. The width of the slab is 3 meters. Since the slab rests on the beam, half of the total weight of the slab is going to be placed on the beam as a distributed load. The intensity of the distributed load is 12.6 kilonewtons per meter. How did I arrive at this value? I multiplied the specific weight of concrete by the thickness of the slab, multiplied the result by 3 meters, the width of the slab, and divided it by 2, since half of the weight is going to be supported by the beam on the other side of the slab. Here is the beam subjected to the distributed load. To determine the support reactions, we are going to write and solve 3 static equilibrium equations. Knowing the reaction forces, we are now ready to write the shear and moment equations. Since there is no point of discontinuity in the applied load, we need only one equation for shear and one equation for bending moment for the entire beam. To write these equations, we cut the beam at an arbitrary point, like this. Let x represent the length of the segment from the left end of the beam to the cut point, so x could vary from 0 to 6. We use V and M to represent the shear and moment at the cut point, respectively. The 2 equilibrium equations for free body diagram are. Solving these equations for V and M gives us the shear and moment equations. Let's summarize what we know. We can describe shear and moment for the beam using these equations. Just like the previous case, the shear equation here does not cover the ends of the beam where the support reactions are located. The moment equation, however, is valid for the entire beam, including its endpoints. Now, let's turn our attention to the side beam. It's subjected to two loads: a concentrated load due to the weight of the staircase and a distributed load due to the weight of the concrete floor. The staircase distributes its load to the supporting beam, which in turn transfers half of the load to the side beam. In our case, we assume the share of the staircase load applied to the beam is 5 kilonewtons. The distributed load due to the weight of the concrete floor is assumed to be 8.4 kilonewtons per meter. The length of the beam is 8 meters, with the concentrated load being applied at its midpoint. Similar to the previous two cases, we start by determining the support reactions. Here is the free body diagram of the beam, and here are the resulting equilibrium equations. The support reactions for the beam are: here, the loads divide the beam into two segments. So we need two sets of shear and moment equations. To come up with the equations for the left half of the beam, we are going to cut the beam at an arbitrary point in the left segment. As usual, the shear and moment at the cut point are labeled V and M. The length of the segment is labeled X, which could take any value between 0 and 4. The resulting equilibrium equations are: solving these equations for V and M, we get the shear and moment equations for the left half of the beam. For the right half of the beam, we cut it at some distance x from the origin, where x could take any value between 4 and 8. This free body diagram results in the following equilibrium equations, which would give us these shear and moment equations. Here is the summary of the results. Now it's your turn. See if you can come up with shear and moment equations for these beams.